Okay, this is MAC 1105, section 3.5, continuing with numbers 6 through 9. This is information for number 5, so we're starting off with this information. Using the transformations of 1 over x, and let me just give you a picture of that so that you will then be able to pick out which of these is the transformation. Okay, so when it's 1 over x, you have a hyperbolic wing right here, right up against the y-axis. Remember, this is considered the parent graph. Okay, when it's just a constant in the top and x to the first degree in the bottom. Or, specifically a 1 in the top. So that's your parent graph. Excuse me. And when we're talking about shifting, we're always talking about it with respect to the parent graph. So if you were seeing all of a sudden a question being asked where they're saying, where has this shifted with respect to this? What you have to think about is your horizontal and your vertical shifts. Whenever it's a horizontal shift, the number will be with the x. And remember, all horizontal shifts, this is from chapter 2, behave the opposite of the number that you're seeing here, of the sign that you're seeing here. So really, you're going to have a horizontal shift of -2. That means you are going to shift left, because you're going towards the negatives, 2 spaces. See, these are the kind of things that are going to help you pick out which of the graphs are. It'll still, remember when you're shifting, it still has the same shape. So you'll have a hyperbolic wing that goes in this direction, another one that's catty corner to it, but it's going to shift 2 spaces to the left. And then a number that is not attached to x, but just a free-floating number out to the end of whatever the particular function is, that's what we call a vertical shift. So you have a horizontal shift 2 spaces to the left, and you have a vertical shift. Remember, with those, you don't switch the sign of +7. That means you're going to be going up 7 spaces. Okay, so that information combined with the horizontal shift. Okay, let's go left 2, up right, up 7. All right, so let's see. Left 2. So this one looks like it's left 2. That's too far. Let's see, that has the wrong vertical shift. I'll just tell you what's wrong with them. This has the wrong horizontal shift. Okay, we were going up 7, that looks like about 7 spaces. And let's see, that looks like about 2. That looks like 2 spaces to the left and 7 up. I'm thinking it's this one. This one has the wrong horizontal shift also. Because see, this one goes, and what I'm looking at, if you're not seeing what I'm looking at the asymptotes. Because when you move the asymptotes, it takes these wings that you're seeing and completely moves them over. So I was looking at this vertical asymptote right here and the fact that it's 2 spaces to the left as we decided the horizontal shift would be. Then I'm looking at the horizontal asymptote, which is right up there, and I see that it's 7 units higher than it typically is. Because look, on the parent graph, this is the horizontal asymptote, the actual x-axis. And the vertical asymptote is the actual y-axis. So when you think about shifting horizontally and vertically, that's really what you're shifting. And this is the one that does it. This has shifted 2 spaces to the left, and the horizontal asymptote is 7 units up in the air. So that was wrong, that was wrong. And B is your answer. Okay, number 7, you're going to do a full graph. Okay, so we have to do it right here. Okay, so the first thing you're going to notice is what makes the denominator equal to 0. That's the first question you should ask yourself, because that could potentially be either a vertical asymptote or a hole. Okay, now remember, a hole is when an expression cancels with the same expression in the top, and that is not happening here because there's no expressions with x in the top. So it can't be a hole, has to be a vertical asymptote, and that's all about what makes the denominator 3. So at x equal to 3, that is the number that you would plug in that would cause a 0 and therefore make this thing undefined. So go to x equal to 3, 1, 2, 3. Drop your vertical asymptote. Then you're going to want to think about your horizontal asymptote. Those came with 3 different rules that went with them. That was all this information at the top of this page. So again, let me review that with you. You see that there's no x's whatsoever at the top. So the power at the top is considered to be 0 because there are 0 x's in the top. I'm using n because that's what they call whatever the highest power is at the top. They refer to it as n, and then the highest power in the bottom, they refer to it as m. Highest power in the bottom is 1. So it is said that when the n value is less than the m value, that means that the x-axis is the horizontal asymptote. So whenever the power at the top is less than the power at the bottom, you don't have to write this out or this out, but I'm just trying to point out to you what I'm looking at. I'm looking at a power of nothing on the top, or 0. I'm looking at a power of 1 on the bottom, and when I compare these two numbers, as these rules up here say, the power on the top is less. And anytime that's true, this x-axis is your horizontal asymptote. If they ask you to name it, this x-axis goes by the name y is equal to 0 because all points on the x-axis have a y value of 0. So this is the actual name of it. But anyway, as far as graphing, there's your horizontal asymptote right there. This is your vertical asymptote. And your graph is going to be positioned inside and to either side of these asymptotes. So you're going to have one piece on the right, one piece on the left, and then one of them stays above, one of them stays below. By the way, you will never, your branches or any part of your graph is never going to break through the vertical asymptote, but it is possible to break through the horizontal asymptote. You can also check the graph on your calculator. You can put into your calculator 4 divided by, and any expression that has more than 2 terms, as this denominator does, you have to put it in parentheses. If you do put that in your calculator, not that you have to, because you can actually do this by hand, you'll see where the branches of the rational graphs is. So like for instance, if I wanted to put it in here, I don't know if I can show you this online. I just put in 4 divided by x minus 3, press graph. There you go. One wing to the right, one wing to the left, and they are above and below the horizontal asymptote, if you can see that, but you can always enter it on your calculator as you work along with me. If you're trying to get these wings by hand and you just wanted to do the calculations yourself, let's say you don't have a calculator, all you do is you pick one value to the right of the vertical asymptote. Like for instance, let's say that I choose, okay, the vertical asymptote is at, well, you should always name your asymptotes. Like this one's called y equal to 0, this one's called x equal to 3, just like it says over here. Okay, so if you did wanted to figure out where these wings are, you have to know that what's on the rightmost end and the leftmost end of these rational graphs are these hyperbolic wings. Sometimes there's a section in the middle, which I believe there is one on this worksheet on the next page, and those shapes that are in the middle are not hyperbolic wings. They're either they look like parabolas or Can also look like the cubic shape. But for right now, when you're talking about the right end and the left end of your graph, they are these hyperbolic wings. So if you wanted to figure out whether this wing is either above or below the horizontal asymptote, you could choose an x value to the right of this, like 4, and plug it into the equation. So then that would be y is equal to 4 over 4 minus 3 which is 4 over 1, or just 4. So when you choose 4, you get a y value of 4, and this is like a point that you can plot to tell whether the hyperbolic wing is up here or up here. Watch, when you plot 4, 4, you're over here. This is the number 4, and then let's just say 4 is up here. You see how when you move to 4, 4, you're up in this region, not down here? That tells you that this hyperbolic wing is up here. And then if you want to pick this, figure out whether this one is below or up here, because there are some graphs, but that has to do with the power changing. I mean, with what you have, they're catty corner. But if you wanted to figure out the value here, you would again think about this vertical asymptote at x equal to 3. Pick a number that's over here, like 2. 2 would be on the left side. You just want to figure out what's the action that's going on over here. Everything over here has x values less than 3, because this is 3 is the dividing wall. So you could choose x equal to 2, and you could plug it into the equation. So 4 over, I chose 2, so it would be 2 minus 3. And you get 4 over negative 1, which is negative 4. Okay, so when choosing 2, the y partner is negative 4. And when you plot those two numbers, see, you'd be out here at 2, negative 4. And even one point is below the x-axis, then all the points on that hyperbolic wing are below the x-axis. And that's how you know that you have one wing down here and one wing up here. These wings, they get very, very close. They get closer and closer and closer to this asymptote and closer to the horizontal asymptote. So they approach those asymptotes until they get closer and closer to them. Okay, so that's the finish of that graph. Number 8. Okay, so let's see. The first thing we're going to do is decide whether we have vertical asymptotes or a hole. By looking at the denominator, you want to think about what makes the denominator equal to 0. So that value would be x equal to 1. Now, since this does not cancel with anything here, because you can't factor what's on the top, that remains together. This is a 2x, but this is an x. So nothing cancels in the bottom because they'd have to match to cancel. So therefore, this truly is a vertical asymptote. And then as far as your horizontal asymptote, you want to think about which of the 3 cases you're in. Oops, just moved that completely. I hope you can still see. Let me see if you can. That still looks pretty good. Okay, back to business. Okay, so with the vertical asymptote, what I wanted to show you is the page that we were looking at before, but again, these are the 3 cases. This says when, remember, n means the power at the top, m means the power at the bottom. So when they're equal, as is the case here, you have to figure out the horizontal asymptote yourself. You have to create it. It's a fraction. Okay, so since the power here matches the power here, you're always looking at just whatever the highest power on each of the numerator as well as the denominator. Then your horizontal asymptote's like this. It is a fraction, and it consists of the coefficients, 2 over 1. Okay, so that is your horizontal asymptote. So you're going to start your graph always with these things. Okay, so right at 1, This will be y, this will be x. You have a vertical asymptote. You should name it as an equation. Don't just put a 1 here, because then we don't know if you're talking about, when you just call it about, like a lot of students will go like this, vertical asymptote, and then they'll just put a 1 here. That doesn't mean anything with respect to graphing, because it's ambiguous as to whether you're talking about the 1 on the x-axis or the 1 on the y-axis. Therefore, it's not a valid answer. So when you are doing anything with graphing, you need a letter, an equal sign, and a number. Okay, so all vertical asymptotes are x is equal to, and then the number that it goes through on the x-axis. The horizontal asymptote is y equal to 2, so go to 2 on the y-axis and draw a horizontal asymptote, and you can name that also. Okay, then you're going to see what kind of shapes you have here and here, or here and here, or possibly there and there. You want to check that out yourself. Again, you can do it in the calculator if you'd like, or you can do what I just told you. If you were going to figure out what's going on over here, I'll do it by hand as well as by calculator. If you wanted to know what's going on to the right of this vertical asymptote, which is at 1, you need to choose an x value that is bigger than 1, so like 2, and then plug it into the equation. The equation is y is equal to 2x minus 1 over x minus 1. I chose to use 2. So this would be 4 minus 1 is 3, and then 2 minus 1 is 1. That gives me 3. So if I wanted to plot a point from this, it would be my choice of x and then the answer that resulted. All right, so if I went to go plot that, let's see, 2 would be over here, so 2, 3. 3 is going to be up here somewhere above 2. So since I have 1 point up in here, that means the entire wing is in here. So if you wanted to complete that wing, just go right up against that vertical asymptote, but don't break through it. And then creep up along that horizontal asymptote. And you can always check. It is possible to break through the horizontal asymptote. You can check with your calculator, or you can do it by hand. I chose a value that was very close to the vertical asymptote. You could also pick one that's way out here and test it, like 10 or 15 or 20. You can go and plug in a number like that to see if it's still above the value of 2. See, right now this answer that I got is above this horizontal asymptote. But if you want to see what it's doing out here as the x values get bigger and bigger, you can pick something like 10 or 15, something way bigger than I picked, and see, do you still get an answer that's higher or bigger than 2? Again, you can check it on the calculator. Let's see what's going on over here on the left side of this vertical asymptote, but by hand. I think I'll do the work here. So I'm going to choose just some x value that is less than 1. I like 0. And then I'm going to see what's going on with respect to the y partner. I'll do that work down here. Again, I'm plugging into the function 2 times x minus 1 over x minus 1. And I'm plugging in my choice of x. This is 0, take away 1 on the top, negative 1. 0, take away 1 on the top, negative 1. So that turns out to be 1. So when I go to plot my point, I'm plotting 0, 1. Okay, so this is 0, and 1 would be here. So there's the point that I'm plotting, 0, positive 1. And since this 1 point is below the horizontal asymptote and to the left of the vertical asymptote, the entire hyperbolic wing and all the points that are on that wing are to the left and below. Okay, so 1 point can represent what's happening in that particular region. The only thing you might want to mess around with, which is why most instructors will suggest that you try more than one value to see what's happening as you go out this way. Like, at -10, let's say, or -15. What's happening as you go further and further out with these negative numbers to see if you're going to bust through this horizontal asymptote. I'll do it in the calculator, and you can do it along with me. Remember, these expressions that have more than one term, you should put them in parentheses. So I'm going to go parenthesis 2x minus 1 on the top, and then my expression on the bottom is x minus 1, so divided by, in parentheses again, x minus 1, close it up, enter, graph. Okay, so that asymptote that we had at 2, it looks like neither one of these breaks below that. I don't know if you could see that or not, but this is the graph. See those, your calculator is not going to show the horizontal asymptotes, although there's some models of the TI that do show it. The TI 83 Plus doesn't show it, but you can see that there's a area of discontinuity right in between those. And this hyperbolic wing is above it, and this one's below it. That's that line y is equal to 2. Okay, so that's your graph. Okay, then in number 9, we are in, again, the same situation. We're trying to find the graph. We're going to find the vertical asymptote first. This does factor. You always want to consider whether this or the top factors, just so you can see whether or not there's anything that cancels. Okay, nothing cancels, so these are truly vertical asymptotes. Because remember, if there's any expression that matches exactly the expression in the top, it's a whole rather than a vertical asymptote. So you always want to think about factoring the top as well as the bottom. Top doesn't factor because it's already in factored form. But anyway, we have a vertical asymptote at the number that would make this 0, which is x equal to 2, as well as the number that would make this equal to 0, which is x equal to -2. So this time we have 2 vertical asymptotes. Next is the horizontal asymptote. That comes in cases, and the cases that were on the previous page say that when the degree of the top is equal to the degree of the bottom, that this is how the horizontal asymptote is found. It's just this coefficient over this coefficient in the form of a fraction. Top coefficient over bottom coefficient, which is 3. Okay, and that is what starts my graph. Just putting those asymptotes in place. So I have 1 at 2, 1 at -2, then I have 1 horizontal asymptote at 3. And you can label them. Horizontal asymptote, it's not just called 3, it's called y is equal to 3. And this is my y-axis, x-axis, and then my vertical asymptotes are here. This one's called x equal to -2, that's one of my vertical asymptotes. This is x equal to +2, it's another vertical asymptote, and we're going to have to figure out what's going on in the middle, on the sides, and on both of the ends. Okay, so I'm going to figure out what's going on over here first. Okay, so let's say that the cutoff is 2. I'm going to pick something bigger than 2 because that represents this area to the right. So vertical asymptote. I'm choosing x equal to 3. I'm going to plug it into the equation. So it's y is equal to 3 times 3 squared over 3 squared minus 4. So here I would get 9, that's my 3 squared, times 9 times 3 again would be 27. Then on the bottom, I would get 9 minus 4, which is 5. So let's see, this would be a little bit bigger than 5. You could always put it in your calculator if you don't like the way it looks and that doesn't relate, but it's a little bit bigger than 5. So 5.4. Okay, so this would be a point that plots as 3. 5.4. Okay, so if you were at 3, you know that this horizontal asymptote is at 3, so 4 and 5. Plotting at 3, 5.4, you're up here somewhere, and because you have a point above the horizontal asymptote and to the right of the vertical asymptote, you have this hyperbolic wing that's right in here. And then you can check on the calculator to see if it cuts through that horizontal asymptote. Then in the middle you're going to have to choose 2 points because the shapes that you can have in the middle will either be this, a parabola looking shape, and it can go either up or down, or if it's not that shape, then you'll have the cubic shape, and it can either go like this or like this. Okay, so what you have to do if you're getting this by hand is that you have to pick a x value that's close to this asymptote and an x value that's close to this asymptote. So I'm going to pick 1 on this side. Okay, this was so that I could figure out the right side. And if I want to figure out the middle, I'll begin to do the work here. I'm going to pick a number that's close to this asymptote and then 1 that's close to this asymptote. When I pick these values, this one and this one, I'm going to pick 1. And I'm also going to choose x equal to, let's see, I'll use -1 as the one that's close to -2. I'll also pick -1. If both of the y values that I get as answer come out up here, then it's an upward parabola. If when I pick these values, 1 and -1, if they both answers come out down here, that means it's a downward parabola. And if I get 1 up here and 1 down here, that means it's one of those cubic shapes, because that means it's going to cut right through the horizontal asymptote. As I was telling you, it's possible to cut through the horizontal asymptote. Okay, so let's see what's happening. At x equal to 1, my y value is 3 times 1 squared over 1 squared minus 4. So that would be 1, this would be 3. This would be 1 take away 4, which is -3. So that answer would come out -1. So the point that you'd be plotting here is when you plug in 1, you get -1. When you plug in 1, you get -1. So let's say 1, -1 is approximately there. And then when you plug in -1, you would get y is equal to 3 times -1 squared. You're going to get the same answer, -1 squared, because you're squaring away the negative. So this would still be 3 on the top. -1 squared is 1 times 3. This would still be a 1 minus 3, which is -3. You would still get -1. So when you go to plot that, you actually have mirror images. Okay, so this would be -1, -1. Okay, so when you go to graph this, shape in there. And then if you want to see what's going on the left side of the graph, you can choose something like -3, -4, whatever you want. I'm going to choose on the right side x equal to -3, and I'm going to see what the y partner is. So now I already chose 3. You saw that because of what you're squaring the x, that the same thing is going to happen whether you put in a +3 or whether you put in a -3. So the same answer that I got right here when I plugged in +3, I'm going to get that same answer over here, which is 5.4. So when you plot -3, 5.4, -3, 5.4 is up here. And if you have even 1 point up here that's above the horizontal asymptote and to the left, then that whole hyperbolic wing that goes through that point, all the points on that wing are up there. Again, you can also get these pieces in your graphing calculator. So you could enter y is equal to, clear out what you have, 3x, put a square on it, divided by x squared minus 4 on the bottom. And you probably need to put parentheses around that. Let me try and fix that. Okay, so I have 3x squared at the top, x squared minus 4 at the bottom. If you have 2 or more terms, put it in parentheses, and then go ahead and graph it. And there you go. I went too high. You could have gotten a third point to make sure that you're staying below. That's why it might be helpful to get a third point in the middle. I should have done a third point in the middle, so let me drop this a little bit. So this goes like this. Okay, and there's your graph. So you could have gotten a point close to this, a point close to that, but I guess I'm sure you're saying already, I'm just going to get the shapes in the calculator because look at how much work it is when you're doing it by hand. But if you do have a part, something in the middle, it probably is wiser to get 3 points just so you don't, go too low or too high with whatever the shape is. Okay, so that completes section 3.5.